Thank you for joining us. I would like to give a warm welcome to you all who have joined us from different time zones throughout the globe. I can track your names and trying to estimate your geographical locations, and it's one of my hobbies before just initiating a Rocscience webinar. My name is Anıl Yunatçı from Geodestek, and on behalf of Rocscience, we'll be running a 3-session seminar today. Thanks for joining us. The total duration is expected to last for an hour and a half. The content during the first 2 sessions will basically cover how a real rock slope stability case is modeled using different approaches and a suite of Rocscience software tools. This includes a kinematic analysis, finite element-based static and dynamic behavior of discontinuity-controlled slope and simulation of rockfall hazards. The 3rd session of the seminar is devoted to a beginner-level assessment of seismic soil slope stability assessments and prediction of seismically induced permanent displacements. First part of the presentation is devoted to evaluation of rock slope stability related risks and seismic performance assessment of slopes in Romania, which is a case study at Cetățuia Hill, Cluj-Napoca. The presentation is to be delivered by Mr. Octavian Bujor from Romania. Mr. Octavian Bujor has an education background in civil engineering and an experience of over 7 years in geotechnical engineering. His main areas of interest are geotechnical monitoring, slope stability, and laboratory testing of soil and rock. Currently, as part of GeoSearch, he leads the team responsible with elaboration of geotechnical reports for multiple highways in Romania. Besides his work at the company, he is also a PhD candidate at Technical University of Cluj-Napoca in geotechnical engineering, where he studies the monitoring and thermomechanical behavior of energy geostructures. He will have a chance to share his extensive field and modeling experience gained during the stability assessment of a selected region in the city of Cluj, representing a historical background on the stability issues encountered at the site. The second part of the seminar will be run by Mr. Ferenc Deak from Budapest University of Technology and Economics. His topic will be earthquake hazard evaluation, probabilistic seismic hazard analysis around Cluj-Napoca city, and dynamic rock slope stability investigation by using RS2. Mr. Ferenc Deak has education background in geology, engineering geology, and an experience of 17 years in geotechnics, underground deposition of radioactive wastes, tunneling, hard and soft rock support, grouting in hard rock, geological site investigation for a new nuclear power plant, in situ rock measurements, slope design, mining, rock mechanical laboratory tests, geotechnical investigations. He is a PhD candidate at Budapest University of Technology and Economics. His ongoing research is based on rock mechanical investigations of the Batapati Deep Geological Radioactive Waste Repository project. He is also currently working at the Mecsek Limited as project engineer. He is working in several seismic survey projects in Hungary, and he is joining the high-level waste, low, intermediate level waste, deep geological repository investigation programs in Hungary. We can't wait to see how this piece of study discusses the criteria for design-based strong ground motion selection and modification to be used in dynamic analysis. Ferenc will also discuss how the numerical model parameters were calibrated using evidence from field blast data. Myself, Anil, is working as an engineer responsible for running several of our geotechnical engineering related operations here at Geodestic. We are located in Middle East Technical University's Technopolis area in Ankara, Turkey, and have been serving the industry by conducting geotechnical investigations, design, quality control services, custom-tailored instrumentation solutions, R&D activities, as well as software-related operations for almost 2 decades. So at least for my humble contribution in today's seminar, a group of our colleagues within Geodestic owe the real credit. Geodestic has been partnering with Rocscience for software sales, educational activities, and technical support in our area and beyond our borders since 2011. And we feel privileged to co-participate in many national and international courses and workshops together with the Toronto office, addressing the geotechnical engineering community with great enthusiasm. We can't wait to travel and meet today's seminar participants in person around our exhibition, course, and conference appearances around the globe, hopefully very soon. Without further ado, I wish to leave the stage to Mr. Octavian Bujor from GeoSearch. We would like to have you on floor for your presentation.
So, dear Anil, thank you for the kind introduction and for the opportunity you gave us to share our experience with the Rocscience softwares. As already Anil told you, our topic for today is the evaluation of rock slope stability related risks and seismic performance assessments on slopes in Romania. Since we are talking about rock slopes from Romania, we considered a very great opportunity to share with you a case study related to the topic of the seminar. As of course, already Anil told you, the presentation will be split in 2 parts. One presented by me, where I make a general description of the site related to our study case from multiple points of view, along with several geotechnical assessments. In the second part, our great partner from Hungary, Mr. Deak Ferenc, will discuss about the importance of seismic assessments and their impact on slope stability. Okay, so this case study presented today is regarding the slope stability analysis of the eastern rock face from Cetățuia Hill from Cluj-Napoca, Romania. Usually in slope stability engineering, in order to be able to offer solution to overcome failures or to mitigate consequences, it's essential to evaluate the hazard and the factors that govern it. So we'll start with the hazard. Regarding the site, there is a very long written history related to the slope failures in both soil and rock, some of them with multiple victims. In the first pictures, you can observe how the certain slope of the Cetățuia Hill starts to be populating, starting with the 17th century. We also have an Erzsébet Híd, which is not so quite and large as the one from Budapest, but we have it. The long history of failure starts from year 1831 and until 1999, where 8 important failures were described in the literature. It is possible that the number to be much greater than this. One of the greatest failures is the one from 1918, where a rock block of around 340 cubic meters destroyed 9 houses and killed 5 people. Another important failure is the one from 1942, where a very great restaurant called Belvedere collapsed. During time, there was multiple projects done on the site in order to increase the factor of safety. Most important of them being done in 1982, as you can see in the picture, where deep drainage systems were installed, but unfortunately not on the entire slope. And in 1999, another important slope failure occurred. So since that last failure, it appeared that the slope is kind in an apparently stable state. But our recent studies of the slope revealed very important aspects that led us to the affirmation there is a matter of time until the next slope failure can happen. Okay, so when we as specialists analyze a slope failure, it is crucial to take into account all the factors that led to the failure. Why I'm saying that? Because analyzing only a specific factor is technically incorrect, since the final factor is nothing more than a trigger that sets a body of work in motion that was already on the verge of failure. For the presented case study, we try to split the factors into two categories, constant and variable. I will talk about each one of the factors. So we have the constant factors, geomorphology, geology, and the structural features, and all the other factors are considered as variable. Regarding the geomorphology, I want to remind that our case study is located in the central part of Cluj-Napoca, Romania. Regarding the geomorphology, we have steep south face slopes ranging from 25 degrees to 90 degrees, which is the rock face. We have moderately steep eastern and gently dipping northern, as you can see in this picture. The cliffs are the one which are highlighted with the black lines. And the one from the most eastern part is the second one from the most eastern. It's our study case. The geology. The geology is one of the most important factors, since on the site we can find multiple soil and rock types. In the upper right picture, you can observe the Gruia formation, which is a sandstone, and in the lower right of the slide, you can observe the Oligocene continental deposits consisting in warped red clays with sand interbedding. Well, we have another multiple structural features, but usually there are in tight connection with the geology. Some of the more important aspects are that there is a northwest dipping of ranging from 6 to 10 degrees for the prime Miocene successions. There is a very important strike slip type fault not far from the site, which is associated with smaller faults but not very well documented. One important aspect that is revealed after the current geotechnical investigations is that there are some faults with almost east-west strikes apparently the slope face. These type of strikes can be viewed in the upper right part of the slide in the picture. There are the red strikes that's dipping into the surface of our 3D model. Regarding the discontinuities, we'll discuss in a few minutes. Regarding the climate and hydrology, it is important to remind that the analyzed slope failures are closely climate related, where late winters and early springs excess counts the most. For example, there are multiple months where precipitation were higher than 100 millimeters in the year of 1970. You can see that usually the median precipitation for that month it's around 90. You can see that, one second, I should put a laser point. You can see that things here that the median from 1961 until 2019, the median precipitation for let's say the summer period, it's around 19. Usually we have some related precipitation with slope failures in the year of 1970, where we have a lot of months that exceeded the 100 millimeter precipitation, and also for the failure which was in 1999. Regarding the hydrology, I want to point that in our study case, the current water level behind the analyzed rock slope is at 33.5 meters below the ground. And during the rock face mapping, the rock face was completely dry, but during periods with abundant precipitations, springs were observed at the sandstone level. I will now cover quickly the variable factors regarding the dynamic loads and anthropic factors. For people outside Romania, I want to remind that according to our seismic norms for Cluj-Napoca, we have a design ground acceleration as part of gravity of 0.1. Even that in recent times, important seismic activity was not recorded, there are some historic evidence which shows larger magnitudes. The first evidence are the Big Six Catalogue, and where historic earthquakes up to 6 moment magnitude seismics were described in the Middle Ages. Another one is described by Kazmer in 2017, where he analyzed the earthquake damage on St. Michael Church. Here you can observe the repair traces of in-plane shift of the adjacent masonry blocks, those white fillings that are just above the Gothic windows. These are the ones we are talking about. And here you can see some displacement and some of the in-plane shifts of the adjacent masonry. Also, in the literature, there is pointing an earthquake foci out southwest of Cluj-Napoca. Here is the Cluj, and here is the foci that it is described by the author in the year of 2000. An interesting aspect regarding the dynamic loads is that prior to failure from 1918, artillery fire was reporting during a celebration. So when you are talking about slope stability, is especially for open pits, it's very important to take into account the dynamic loads that have a different source for comparing to the seismic one. The anthropic factors, what we can say about that, it is very well known worldwide that one of the most important factors that trigger the slope failure is the human. As you can see, abandoned construction sites and excavation were present on the slope during history. Some of them are even now left abandoned. For the present project, an extensive campaign was done where multiple types of investigation were done, such as geotechnical boreholes up to 42 meters depth, geophysical profiles. We have conducted 4 geophysical profiles, the drone mapping. I can let 15 seconds presentation of our drone mapping and the 3D model we have conducted in order to extract the discontinuities. And of course, one of the most important for the future investigation for the future of the slope, the geotechnical monitoring. I will now present the geotechnical assessments of the rock slope and how software from Rocscience helped us in our work. First of all, I want to say that we treat the slope stability from 2 points of view regarding the type of analysis. The first one is the kinematic one, where we use dips from Rocscience in order to establish the geometrical relation between dipping planes and rockfall to simulate rock falls from different points of the rock face. The second type of analysis is the numerical one, where finite elemental analysis were conducted using software from Rocscience as RS2, considering multiple failure criteria as Hugh-Brown and Barton boundaries for the joints. So we will start with the kinematic analysis, the simplest one from dips. As a preliminary analysis of rock stability, we used dips. As most of you know, one of the first steps in rock slope stability is to analyze the discontinuities. For the present project, we used a different method. We used regarding to the conventional field observation. We used the photogrammetry method because of multiple considerations. So what I want to point is that the main difference between the conventional field observation and photogrammetry is the number of discontinuities that you can extract. We used for the present project the discontinuity extractor software, which is an open source software. You can find it very easily online with a simple search on Google. And you can see that the photogrammetry produces a very large number of discontinuity cluster orientation compared to the mapping procedure. How we done this is the following. In the first stage, the raw photos were aligned and a preliminary model was created. In the next step, the preliminary model was referenced by landmarks that could be observed in our small video. Yeah. And after that, the orthophoto image is produced, on the basis of which the subsequent analyses were performed. So we could extract, with the help of discontinuous set extractor, a large set of discontinuities. We have around 200,000 discontinuities, which we are implementing in the DEEPs. So DEEPs is one of the most straightforward software to use for the Rocscience. You need only the azimuth, angle, or deep dive direction, trend, plunge. It's only a matter of preferences. How do you want to work with the values? We usually work with deep and deep direction. After you are introducing the discontinuities in the software, you can make some kinematic analysis. So, regarding the planar sliding, you can observe for a slope deep, which is considered to be 65, and a slope deep direction, which is considered 160 degrees, a friction angle of 32 degrees, and a lateral limit of 20 degrees, we obtain a planar sliding in case of around 12% from the all discontinuities. So it is a quite small percent, so statistically saying. Regarding one of the most important failures, the wedge sliding, we are happy to see that we have 0% type of wedge sliding. Regarding the flexural ones, we can observe that we have around 8%. And in the case of base plane types of failure, we have a bigger percent, which is a percent around 26. Well, you can see here that the direct toppling intersection, oblique toppling intersection is with 0%. Why is that? Is because with so many discontinuities implemented in the DEEPs, the software is unable to make the intersection. So it's written here an error that are too many entries for the grid intersections. So I will not go into detail how we manage this, but you have to make a statistical analysis of the number of the discontinuous extracted, and based on engineering judgment, you have to reduce those numbers to have a smaller amount of discontinuities in order to also can extract from the DEEPs the direct toppling and oblique toppling intersection type of failures. Also, what I like at DEEPs is that you can have a 3D model. So after I just put here two sets of discontinuities. So in order to have a better understanding of the discontinuities all the time, after you make a family of discontinuities, you can view the family in the 3D. So it can be very, very, very useful for people who are at their beginning with this type of failures and with working in DEEPs. And I just put a photo for people who are not very familiar with the types of failure that can occur in rocks. Just to remind that we can have plane failure, wedge failure, circular failure, toppling failure, and of course the direct failure, which is not as part of this picture. Before I go to the following analysis, I want to point some of the most common misuses regarding the stereographic projections. First, and the most important one, is that DEEPs are used sometimes as a stability analysis tool rather than a tool used to sort discontinuities and identify what further analysis is required. For example, if you want to analyze the wedge failures, another software must be used. In case of Rocscience suite, you can use S-wedge software in order to obtain a factor of safety based on liquid element method. Okay. So Another things that can be very tricky when you are going to make a mapping of this rock phase is that sometimes you can contour too few and unrepresentative discontinuities measurements. So it's all the time better to, based on your engineering judgment, to see if your colleague from the field, or if you went yourself on the field, and if those discontinuities measurements you are contouring are very reliable for your stability analysis. And one of the most important that is that contouring can hide important discontinuities as faults that are not part of this continuity set. So you should keep in mind that DEEPS has its limitation, and for further analysis, another types of softwares must be used. Okay, so regarding the rockfall simulation, since near the rock face there are pedestrian alleys, the hazard of rockfalls was needed to be taken into account. Rockfall simulation was done using rockfall. In the following pictures, you can see the trajectories of the rock detection from different points. For rocks with a mass of 1,000 kilograms, 1 tons per rock mass. Imagine that it is not a big one. It's maybe 1 meter per 1 meter, and with a height of 0.5 meters. It has a very high total kinetic energy. You can reach a total kinetic energy for a rock with a mass of 1,000 kilograms of 0.12 megajoules. Imagine that a kinetic energy of a driving car with around 50 kilometers per hour, it's around the same amount of kinetic energy as this simulation. So if we are to consider the failure from 1918, where 340 cubic meters rock mass was involved in a falling, you can imagine the magnitude of the disaster that was created in the history. And also from the rockfall simulation, you can have multiple types of envelopes. I put here the rotational kinetic energy envelope. You can have the height of the rocks which are falling and bouncing, and multiple types of analysis. I will not go into detail because it's not the main topic of our webinar. So for the second type of analysis, in order to obtain a more precise slope stability evaluation, the SSR method implemented in RS2 was used, where Hugh-Brown failure criteria parameters were chosen as failure criteria failure criteria parameters for the materials. And in order to give those parameters needed for the Hugh-Brown failure criteria, we used rock data. From my point of view, rock data, it's one of the simplest software that Rocscience has, because you have to introduce the unconfined compressive strength of your rocks. For example, in our case, we considered an UCS values of 50. You have to consider the geological strength index of the rock mass, and for the present study case, we considered it around 16. And you have to consider another very important parameters, which are the MI constant and the Young modulus of the intact rock. Well, here we had a problem because we are not able to do extensive tests in order to determine the MI parameters and the Young modulus. And what we have done is that since we are not able to determine in the laboratory the MI constant and Young modulus for the intact rock, we use the rock probe database, which is implemented in rock data updated RS data currently. and choose a statistic value on the safe side from similar sandstones around the world. In the pictures, you can find here, there's this, for example, we have a sandstone which has an MI constant of 13, and which is a very good correlation of 0.198. So we analyzed multiple types of sandstones and choose a value for the MI of 12 and a value for the intact modulus rock of 15,000 or 15 gigapascals. The disturbance factor was set to 0, and the application was set for a slope with 20 meters height. From rock data, you can have as output multiple parameters. First of all, you can have the parameters needed for the Hugh-Brown criteria, which are the MB, S, A, which are over here. You can obtain the rock mass parameters, which are reduced based on the GSI and the GSI. And of course, you can have the basic Moore-Coulomb parameters, since in current days, they are still probably the most used parameters in both soil and rock slope stability analysis. You can observe here that for the Moore-Coulomb fit, you have the cohesion and the friction angle. Since Moore-Coulomb envelope does not consider the non-linearity of the shear strength, it is recommended to choose in software the Hugh-Brown failure criteria as input parameters for materials where rock slopes are involved. Parameters obtained were used in the following analysis conducted in RS2, analysis which will be presented by Mr. Deak in the second part of the webinar. Also, maybe he will have time to speak about the Barton-Bundy's failure criteria for the joints. I did not put this into my presentation. So I want to thank you all for your attention, and please feel free to ask me any question, preferably to mail, in order to get a more comprehensive and technical response. I also want to thank you to my colleague, Edward Andras, for the help with the presentation. Unfortunately, he was able to join us today. Thank you a lot. I will now try to switch to, one second, I'll put Ferenc as a presenter. And if there are any questions regarding my presentation, please feel free to ask, and I will try to answer now during Ferenc presentation. Thank you a lot.
Dear audience, greetings from Hungary. It is a great honor to be able to talk to you about the results of our previous researches. And Anil, thank you for the introduction. My first encounter with the Rocscience software family was in 2004. Since then, I have been solving a lot of tasks with these programs. And I am pleased to see that the programs have undergone many developments recently. One such key development is the creation of a dynamic engine in RS2 and RS3 codes. Now I want to focus on this topic, especially in the case of RS2. I have been working with GeoSearch company in Romania on two important projects. Recently was carried out in 2019. An earthquake study had to be prepared for the entire road network of the Cluj-Napoca ring road, with particular detail on the area of the planned tunnels. Then in 2020, I conducted a study on the rock slopes of Cetetsuya, where static and dynamic modeling had to be done. In my presentation, I will not go into all the theoretical and practical backgrounds describing the dynamic engine of Rocscience software, as these can be found in more details in the web help, and a longer webinar lecture on this was given by Dr. Qin Deng in 28 October 2020. What I would like to talk about the most is the conduct of a site-specific investigation, especially in the case of earthquakes. If we are already performing well-developed numerical modeling, we should also pay special attention to the production of adequate and accurate earthquake time histories. Don't be content with using unknown time series, perhaps just the envelope curve of the response spectrum defined by a few points offered by different standards, from which, to put it simply, we may produce synthetic time series for our work. Perform a complex and careful seismic hazard evaluation from which we can create much more reliable models by obtaining correct time series. This is important, so I will talk about this briefly. Here are just some points of our issues from the previous earthquake evaluation that I mentioned. Here we carried out a probabilistic seismic hazard analysis. And just some words let me say about this. So the term probabilistic seismic hazard analysis in a broader sense is used for all seismic hazard analysis methods which attempt to define either the frequency of events of earthquakes or the frequency of exceedance of secondary parameters. For example, specified ground motion levels. In general, any probabilistic hazard analysis method includes the following steps. You can see here a step. At the first step, it's important to make the source scenario, then magnitude recurrence relation calculations, then to choose a good and accurate attenuation relation. Then as a final processing procedure, we can get as final results the seismic hazard curves and of course the response spectra. One of the most important products of seismology is Earthquake Catalogue, which provides a broad data set in earthquakes events. This can be used in various analyses associated with seismicity and seismotectonic hazard assessment and physics of earthquake. Earthquake catalogues are treated by two steps, mainly. The clustering of earthquake catalog and determination of the minimum magnitude of completeness. The clustering seismicity is the method to sort out main shocks, foreshocks, and aftershocks in the catalog and removal of dependent events. Particularly, this technique is applied in earthquake prediction models and seismic hazard assessment. And maybe an important equation is here. This is the Gutenberg and Richter equation. Here you can see a worldwide earthquake hazard map. Here is Romania. Romania has one of the highest seismic hazard levels in Europe. A recent study by Pavel et al. 2016 shows that around 2/3 of the country has an expected peak ground acceleration in excess of 0.2 g. So this value is with 10% probability of exceedance in 50 years. Because the lack of time, we have no chance to explain the complex geotectonic and geological background. Just I would like to pay your attention that here is a important region, so mainly is the Vrancea region, which is very similar to the Hindu Kush region. Here is a profile, seismic tomography profile with the hypocenters. Here is also based on this information, it's visible, and there is a possibility to visualize how it's downing into the Earth's mantle, the continental slab at the Vrancea area. So that's why we have very deep hypocenters also, and middle depth, and of course shallow depth earthquakes in this region. Repeated large and intermediate depth earthquakes in Vrancea region shake several times central and eastern European cities, several hundred kilometers away from the hypocenter. So it's very important. Let's see some three-dimensional visualizations on this slab. Here is a 3D model based on 3D thermal investigation. Here you can see also a geological time scaling. So on the evolution of this enormous body. And here is another model based on seismic tomographic information, with the circles and asterisks are indicated the location of the magnitude of the seismic events. And just some information for our probabilistic seismic hazard evaluation. So we used mainly two important catalogues, the Big Cs and the ROM+, in our work until 2019, but I made also an update, so now we have until 2020. These are free catalogs. And during our work, we also made a checking by a special Hungarian catalog, and all are in the right place, and all parameters are correct in our models. Source models were used, the Big Cs and the share model. So Big Cs is mainly used in Romania, and share is used all around Europe. And as background studies, Deak et al. And Pavel et al. Materials were used. Here you can see the used area sources during our modeling. This is the Big Cs and this is the share. So we have to mention that we didn't use faults as line sources or other point sources, so just area sources were used. And let's see, the declustering was carried out by using ZMap code. This code is using the Gartner and Knopf algorithm with the original window parameters. The declusterization was carried out by using this code. And of course, here at the right side, you can see a figure on the frequency magnitude distribution without declusterization. And here it's visible the results after the declusterization with the Big C's source areas. The probabilistic seismic hazard calculations were solved by using the crisis free program. This program employs a probabilistic methodology to assess seismic hazard in regions. The required input data for crisis are the geometry of the seismogenetic sources, the seismicity parameters of the sources, and the ground motion prediction equations for seismic intensities. Each seismogenetic source can be represented by means of different geometrical models, such as areas, lines, or points. But as I mentioned, we use just areas. The seismicity of the sources can be considered either by Poissonian or non-Poissonian models. The seismic hazard assessment is performed for a grid which characteristics in terms of spacing and shape are user-defined. And of course, the main equation used by Crisis is the original Gutenberg and Richter equation and a specific modified Gutenberg-Richter relationship, which calculates the annual rate of exceedance. Of course, to calculate the intensity exceedance rates in Crisis, it is required the following. To define the zones where earthquakes are occur, seismogenetic sources, assign the magnitude recurrence relationships for each seismogenetic source, assign the ground motion prediction equation to each seismogenetic sources, and finally processing final results. Result is a hazard map, and by intersecting points we can download the hazard response spectra and the intensity curves. Of course, during the processing we have possibilities to use a more accurate and complex probabilistic evaluation. For this, during the probabilistic calculations are used logic trees. In our case, I used a complex logic tree where the big C's model had 0.7 weight and share 0.3 weight. And of course, the big C's branch system is very similar to the Powell logic, to the logic tree used by Powell et al. But at the end, the branches are a bit changed, and of course, all ground motion prediction equations were changed to new and recent equations. In the case of shear branch, used a similar logic tree as we used in Hungary in a previous work. As I mentioned, we have at the final result a map, and anywhere if you make a click, we can export the hazard curve and the response spectra too. However, as a result of the study carried out in the framework of this project, the bedrock P-ground acceleration and the response spectrum were calculated for entire Cluj-Napoca area, which were summarized in a map appendix, which maps were prepared by using QGIS. So we have selected the response time periods required for the construction of the design spectrum for future design work in accordance with the requirements of both Eurocode 8 and the Romanian regulations. These are the following response time periods: 0, 0.05, 0.07, 0.15, 0.4, 0.7, 2, and 3 seconds. For the following return periods were used: 95, 225, and 475 years. And another step is the site amplification. Seismic waves generally travel several kilometers in rock, but a few meters in soil. Yet the soil plays a very important role in determining the characteristics of ground motion and its analysis. The local soil conditions have a profound influence on the ground's response during the earthquake. Ground response effects are generally evaluated using one-dimensional models, which assumes the seismic waves are propagating in vertical direction through the horizontal layers of the soil. theoretical modeling of one-dimensional site response can generally be accomplished using equivalent linear or nonlinear analysis. Equivalent linear ground response modeling is widely used in practice to simulate true nonlinear soil behavior. The advantages of equivalent linear modeling include small computational effort and few input parameters. The most commonly used equivalent linear computer codes are, example, the shake, the deep soil, the proshakes, so we are using generally the deep soil. And of course, here you can see a figure on the concept of earthquake response spectra. So you can imagine if is coming an earthquake, you have several oscillators. You can imagine that these could be buildings with different resonant frequencies. And of course, it's visible. You have to imagine that, example, the measuring tool, the seismometers are at the top of the buildings, and you will have different time series for different buildings, and of course with different frequencies. A kind of reverse work like the site amplification is deconvolution. In this case, you are going from the top to the deep parts of the model. So typically, we can get some measurements carried out from the Earth's surface, and if we have bedrock, we can assume that should be the same in the deep seismograms and the surface one. In this case, we have a possibility in RS2 and RS3 to use. Of course, user can input the seismic motion with using two options: a rigid base, where input motion, acceleration, velocity, or displacement is applied directly to the nodes, to the mesh. The base still reflects the downwards wave propagation back to the model. A compliant base, where compliance will be activated when users select the compliance base option in the dynamic loading dialog. When compliance base option is selected, the applied motion will be transformed to applied force in this case. The choice of rigid or compliance base depends on whether the earthquake motion to be applied at the base of the model is outcrop motion or within motion. Outcrop motion are recorded on top of the rock layer, as I mentioned before, while within motion are either recorded at a specific depth from soil surface or computed by performing site response analysis. So in our case, if we have a calculated bedrock informational bedrock response spectra, then we can get directly good time series. And let's see how it's working in the models. We have here an example, a project from Hungary. This is a slope, and generally we are using dynamic loads in XY direction too in the same time. But in this case, to check this opportunity, we use just the horizontal accelerations. And Let's see the results. So we check this point here, and we check the x acceleration. And let's see, we have mainly around the maximum amplitude around 3.5 and 3.2 in this case. Of course, we had on this project also a deep soil, a calculation by using deep soil. Here you can see the profile used here with the layers, and of course we can check that at the surface we have around 0.4 and 0.35 values. This is the response spectra summarization. So here is around 0.35. And let's see our deconvolution model. So at the beginning, at the first model, we introduced time history at the top here, but in this case we introduced acceleration, and in the results we exported data from this point, but the velocity data, and then we divide it with 2 because this option converts the then inputted velocity data to stress. So then at this model, in this model, we introduce the dynamic load here at the base. So this is the divided velocities. Here you can see, and we use compliant base with drift correction, of course. And let's see the results. Yes, here we used 100 sec for the time. And let's see now the acceleration again. And you can see that it's very similar, so around 0.3 G, 0.4, 0.35. Let's turn back to the presentation. And as a next step, we also used the calculated response spectra as target spectra for the next steps. In the next step, we downloaded some real measured time series from the online database from the Pacific Earthquake Engineering Research Center NGA West 2 database. And in this case, it makes a searching for the target spectrum, and typically we download 30 real accelerometers, and at the final detailed work we are using mainly just 5 time histories for this work. We are typically using the Seismomatch, so we have to make scaling work and then a matching work. And here is the final site amplification result on the tunnel areas. This is beside the Cluj city. At every site we had downhole measurements. Here you can see the threshold point. So here is the from this depth we have the bedrock around 30 meters in this case. So the bedrock is the threshold is at the 760 meter per sec velocity, shear wave velocity data based on the Euro code, and of course after all evaluations we have this surface response spectra for this area, for the tunnel area. But for the slope stability for the Cseteszuya site, we calculated, of course, the bedrock response spectrum, and it was clear that also because we have rocks, we could use the calculated bedrock spectrums without site amplifications. In this case, so where we have scaled and matched time series, there we have chance to use also the downloaded vertical time series, matched time series, because always we have the measurements in XYZ directions. But in this case, where we don't use real measured time series, there is a possibility to calculate from the horizontal response spectra the vertical one with a empirical equation. Of course, from numerous exported crude compare modeling profiles was one chosen for the RS2 model. This profile is situated at the middle of the part of the this slope you can see here. And for the models, hybrid models, where we used also discontinuities, we also checked some typical discontinuity sets from the original engineering, geological, or geotechnical mappings. And during the numerical modeling, we use the main reason to operate with the factor of safety above 1.0. So another basic was the Eurocode 7 standard. Eurocode 7 represents a major change in design philosophy. With the Eurocode 7, partial factor of safety are applied to different components of the analysis. The partial factors are applied prior to the analysis of given design values. The final result is an over-design factor which must be greater than 1 to ensure the serviceability limit state requirement is satisfied in this case. During the modeling, we tried several model runs using homogeneous material model, and with several variations we tried to introduce the documented discontinuity, as I mentioned earlier. Here you can see the models by using the discontinuity sets. Since that is not the focus of our presentation, I will not go into details, but once the model has been constructed, the shear strengths of all the component materials are iteratively increased or decreased by strength reduction factor until the slope fails. So we used the SRF solution, and we had stable slopes during the static work. For the dynamic investigations, we use the following time series. This is the horizontal, this is the vertical one. Also, in the past, we had to use several other specific softwares to make base corrections, to solve the filtering issues. But actually, in the Rocscience now we have a developed engine which makes possible to solve these issues you will see later on. So you can use the filter spectrum, baseline correction, filter data analysis, and to visualize amplitudes, also response spectra and areas intensity. During our modeling, we used 3 time queries, so 3 monitoring points. And during the continuum models, we had as final results accelerations and other seismograms without noises, and very similar to the original one, so to the input data. Then, in the case of hybrid models, where we introduced discontinuities, when the joint systems are used in the models, the behavior of the rock mass is different, as it happened at the previous case where we were using continuous material. In the case of the hybrid models, where are introduced the joint systems, the models not be discrete models, so the separated blocks have not independent degree of movement, but the discontinuities are behaving as boundaries between the separated continuous areas. The stress redistribution on the discontinuity boundaries is solved, and the physical conditions of the discontinuities are defined at a different solver than the continuous material. This behavior fact is also observable when it is used the dynamic examination. So the attenuation and amplification of the waves is blocked or staggered abruptly as the pass through the discontinuities, and this result is visible here exactly. And how looks like the models. So this is in the first case we just used the horizontal, and then together with the vertical and horizontal, you can see here. And at the end, let me show just some calibration modeling work, because it was very important to us to check some results from our from other researches. And here is the first case when in the Batopati repository project we tried to use measured blasting acceleration time histories, and then together with earthquake we checked the extension of the excavation damage zone, so the change in the extension. And just some words about the models. So firstly, we had here the measurement point, and from here we made an amplification for the blasting time history, and then we loaded the tunnel wall, and then with using a Rayleigh damping of the previous amplified blasting time history, we rechecked the results, and you can see the final results, how it looks like. You have to mention also that the damping of the soils and rocks is independent of the loading frequency. By contrast, Rayleigh damping formulation is frequency dependent and adequate to solve numerical damping. Use of Rayleigh damping in the numerical models allows the user to define the damping ratio for two thresholds frequency. Has a damping ratio lower than the specified damping ratios, and frequencies outside this range are damped more heavily. Numerous variation of the two frequencies and damping ratios were modeled, and the more appropriate result was set to the measured one, in our case, of course. And what is important that, of course, during the measurement, the conventional work, tunnel work, was interrupted in both tunnels, and the ventilation system was turned off. So we could be considered seismically silent in the tunnels. So here is the 2 points, and let's see how looks like the model in reality. We can see that during the blasting we had very high frequencies. Here you can see on the spectrograms, and here you can see the final results. So on Excel it's more visible, so it's very similar. Just we had some noises in our results. Let's see another model. The amplitudes are very similar. And this is how it looks like the model. It was an interesting situation because so for this kind of models we need to prepare a statically stable model, and then we start to input the dynamic loads. So here are the blasting loads, and then outside on the model we introduced the horizontal and vertical accelerations at the same time. And I would like to show you a final final calibration model. So this is from China. We search for some special tunneling information regarding to the earthquake studies, and we have a article from 2016 about the Longxi Tunnel, and we were we were very appreciated to the Chinese specialists, because they sent us the real measured time histories near to the tunnel. So it was a very good possibility to make a calibration on the earthquake issues. The Longxi Tunnel is located at a distance of 2 kilometers from the epicenter of Wenchuan earthquake. So here you can see the total length of the tunnel is around 3.6 kilometers, with a cross-section composed of 2 parallel twin tunnels, one for each direction, separated 30 meters between axes. And what is important that you can see here the they used the rock support system mainly at this area near to the main fault. It was used shotcrete layers and also the pavement, a concrete layer with thickness 43 centimeters. The rock mass along the tunnel is organized into 3 classes based on the Chinese code, and also based on this information and based on the rock mechanical laboratory information, we made a parameterization of our model. The Longsy tunnel, one of the most damaged tunnel is one of the most damaged tunnel during the Wenchuan earthquake. Suffered from small to heavy damage both at the portal and inside the tunnel, while sections close to the fault completely collapsed. This is important. The damage along the tunnel lining, according to the field investigation, is described in detail in the article, so I will not discuss on it more. We concentrate now on the fault area, where heavy damage occurred along the zone about 50 meters from the fault, where the rock mass class was 3. So here is. What is important that the authors used for the investigation the Abacus code, and in the Chinese investigation were considered 3 scenarios, one horizontal so one horizontal motion only was used in the x direction. So in this case, x direction is here and z direction is here. And what is important that if we take into the consideration this fact, so at the Wolong Observatory we had a north-south direction and a east-west direction, and of course an up-down direction seismograms. So this is important if we put the whole system in space. Then they used another modeling, both horizontal X and Z motions, transverse and longitudinal to the tunnel axis were considered without vertical accelerations, and all 3 motions at the third option. This is done to individually investigate the effects of the longitudinal and vertical accelerations on the response of the tunnel, since for the design those are often neglected in reality. So I also mentioned that it's very, very important to use not just horizontal but also the vertical one too. And let's see how looks like our model. So this is an exported section from the Abacus software, and here is the photo on this region. So where is not collapsed the tunnel, there they observed at the tunnel also compression and tension areas. And in this model you can see that here they in the reality and also in the modeling, they had a 2.9 centimeter uplift at the time of 13 seconds. And let's see our model. This is the model. So with the rock support, here are some time queries, some monitoring points. You can see also the horizontal and vertical information. Here I have to mention that we had a simplification mainly. We have to mention that because the tunnel axis is not aligned with the direction of motion recorded, as I mentioned earlier, at the Wolong station, it makes an angle of 33 degrees with the horizontal east-west direction, and 57 degrees with the north-south direction. So the horizontal X and the Z input motions are obtained by orthogonal decomposition of the recorded east-west and north-south accelerations. So our simplification is that we excluded this fact. So mainly we use our modeling the east-west direction and the up-down direction. And what final result we had, you can see here the maximum vertical displacements, and let's see the results. So the vertical displacement, let's see on the plot. So this is, and we can see here. So firstly, we used no drift correction, and then we had 2.85 centimeter between the minimum maximum displacement. So, but it's important that between 20 and 40 second. But at the second correct model, we use drift correction, and we have got 2.02 centimeter between minimum maximum displacements and between 7 and 12 secundum. So it's very similar result as came from China. And dear audience, thank you for your attention.